All right, let's talk about the secret sauce, the invisible engine that keeps the modern internet running. I'm talking about load balancing. It's the real reason your favorite huge websites don't just, collapse under pressure. And today, we're going to pull back the curtain and see exactly how it all works.
So have you ever really stopped to think about it? How in the world do giants like Google or Netflix or you name it handle millions, literally millions of people all at once without just crashing and burning? It's definitely not one single giant supercomputer hiding in a basement somewhere. Nope. The secret is all about spreading the love, intelligently distributing that massive workload. And that, right there, is the core problem that load balancing was born to solve.
Okay, so let's say your app suddenly gets super popular. Great problem to have, right? But now you've got a big choice to make. How are you going to handle all that new traffic? It really boils down to two fundamental philosophies.
On one hand, you've got what's called vertical scaling. This is kind of like beefing up your gaming PC. You just buy a bigger, badder, more powerful server. More CPU, more RAM, the whole deal. But you can see the problem, right? You eventually hit a wall, a hard physical limit, and it gets crazy expensive. So on the other hand, you have horizontal scaling. Instead of one giant server, you just add more servers. A whole fleet of them. They don't have to be top of the line, just standard everyday machines. This is how the big tech companies do it, because it lets them scale out almost infinitely. But it creates a brand new puzzle. How on earth do you manage all the traffic going to all those different machines?
And that's where our hero of the day comes in. To manage that chaos, to direct all that traffic across your big fleet of servers, you need a director, a traffic cop for the internet. You need a load balancer.
So what is this thing really? At its core, a load balancer, and it can be a piece of hardware or just software, sits right in front of all your servers. It acts like a receptionist. When a request comes in, the load balancer looks at all the available servers and says, okay, you go to server A, you go to server C. Its main job, its whole reason for being, is to make sure no single server gets totally slammed. It just spreads the work out nice and even. This keeps everything fast, efficient, and most importantly, keeps your application from crashing.
And here's something you might not realize. It's not just one big load balancer at the front door. Oh no. In any serious modern application, these things are everywhere. You'll find one between you, the user, and the main application servers. Then you'll find another one between those application servers and the caching layer. And heck, you'll probably find another one between the cache and the databases. Basically, anywhere you have a group, a pool of resources doing a job, you're going to find a load balancer playing traffic cop.
Okay, so this traffic cop, how does it actually decide who goes where? It's not just pointing randomly, right? Of course not. The load balancer follows a rulebook, a set of instructions we call algorithms. And these algorithms basically fall into two big camps, static and dynamic.
Let's start with static algorithms. The name kind of gives it away. These are the simple, predictable ones. They work based on a fixed set of rules that you configure beforehand. And the key thing to remember here is that they don't check how busy the servers are. They just follow the plan no matter what.
The classic example here is called round robin. It's exactly as simple as it sounds. The first request goes to server A, the second to server B, the third to server C, and then it just loops back to A. Easy. Then you've got weighted round robin, which is a little smarter. If server A is a beast and server B is kind of wimpy, you can tell it, hey, send more traffic to server A. And then there's something called hash-based. We're going to dive way deeper into this one in a bit, but the gist is it uses some info about you, like your IP address, to make sure you always get sent to the exact same server every time you visit.
Now, on the complete opposite side of the spectrum, you have the dynamic algorithms. These guys are the smart ones. They're not just blindly following a list. They're actively watching the servers, checking their health, seeing how busy they are, and using all that live, real-time data to make decisions from one moment to the next.
So a couple of popular ones here are least connections, where the load balancer is basically asking, all right, who's got the fewest people in line right now? You? Okay, the next request goes to you. Then there's lowest response time, which is all about speed. It sends the new request to whichever server is currently responding the fastest. You can see how both of these are totally focused on giving the user the best possible experience in that exact moment.
So at the end of the day, it's a classic trade-off, right? The static methods, like good old round robin, they're super simple, easy to set up, and predictable. But they're completely blind. If a server is struggling, they'll just keep sending traffic to it anyway. The dynamic methods are way more adaptive. They're always trying to optimize for performance. But that intelligence comes at a price. They're more complex, and they need all this extra monitoring to work. Okay, now I want to circle back to one of those algorithms we mentioned, the hash-based one.
because this little guy solves a huge, huge problem in how big systems work. I'm talking about caching. And this, my friends, is where load balancing gets really clever.
Just think about it for a second. Let's say you visit a website. The server you hit has to go do some work, maybe pull your profile from a database. To be efficient, it saves, or caches, that profile in its own memory. That way, the next time you click something, it's bam, super fast, because the data is right there. But what happens if you're using a simple round-robin load balancer? Your next click might go to a totally different server, and that server has no idea who you are. It doesn't have your profile cached. So all that performance benefit, poof, gone. You really, really want to hit the same server every time.
So the simple, naive solution is to use that hash-based logic. The load balancer takes something unique about you, like your user ID, runs it through a hash function, which spits out a big number. Then it does a little bit of math. It uses the modulo operator, which is just a fancy way of saying find the remainder after division against the total number of servers. And voila, the same user ID will always land on the same server. Sounds perfect, doesn't it? Well, there's a catch, a big one.
Yeah, there's a really catastrophic flaw hiding in that simple math. Because in the real world, things aren't static. Servers fail. Or, if you're successful, you're constantly adding new servers to handle more traffic. So, what happens to our perfect little formula when that number, the total number of servers, changes?
It's a complete disaster. The moment you change that n, that number of servers, the result of the modulo math changes for pretty much every single user. It's a total reshuffle. Suddenly, almost everyone is being sent to a brand new server that knows nothing about them. Every single one of those valuable, performance-boosting caches you've built up across the entire system, instantly worthless. It's called a cache stampede, and it can bring your whole application to a crawl.
So, how do we fix this mess? With a beautifully elegant solution called consistent hashing. Now, instead of thinking about servers in a line, I want you to picture a circle, like a clock face. This ring represents every possible hash value. Now you take your servers and you hash them, and you place them at various points on this ring. Then you take a user request, you hash it, and you place it on the ring. To figure out which server gets the request, you just start at the request's position and walk clockwise around the ring until you bump into a server. That's its home.
And here's the magic. Now what happens when you add a new server? You just hash it and plop it onto the ring. It only affects a small slice of the pie. It only takes over the requests that are immediately counterclockwise from it, the ones that were previously going to its next-door neighbor. Everybody else, they keep going to the exact same server they were going to before. The vast, vast majority of your cache is preserved. It's an absolutely brilliant solution, and it's why consistent hashing is so fundamental to building massive, scalable systems that can grow and shrink without falling apart.
All right, so this is great. We have our army of servers, we have a super smart load balancer directing traffic, but wait a minute. We've just created a new problem, haven't we? We'd introduced a single point of failure. If that one load balancer dies, everything goes down with it. The entire application is dead in the water. So, what's the plan for that? Well, there are basically two popular ways to handle this. The first is an active-active setup. Here, you have multiple load balancers all working at the same time, sharing the load. The big pro here is you get more performance, more throughput. The con is that it can be a bit tricky to keep track of what's going on, since your stats are split. The other approach is active-passive. You have one main load balancer doing all the work, and a second one just sitting there, on standby, waiting. If the main one fails, the passive one instantly takes over. This is way simpler to manage, but the downside is you're paying for hardware that's just sitting there doing nothing most of the time.
Okay, let's wrap this up with the key takeaways. First, if you're going to scale out with lots of servers, which you are, a load balancer is non-negotiable. Second, the brains of that load balancer are its algorithms, which come in two flavors: the simple, dumb, static ones, and the clever, smart, dynamic ones. Third, and this is a big one, if you care about caching performance, consistent hashing is an absolute game changer. And finally, don't forget that your load balancer needs a backup. You have to plan for failure to avoid creating a single point of failure.
And that leaves us with one final thought, a question for the future. In today's world of the cloud and auto-scaling, the number of servers in a fleet can change literally every minute. So how do these classic ideas, these algorithms we've talked about, have to evolve to handle a system that is in a constant state of flux? That's one of the big challenges for system designers today. Something to think about. Thanks for tuning in.